Welcome back to lovely Rio de Janeiro for the 2016 Olympics. I'm just kidding, that would be far more interesting than what we have to talk about here, chemical reactions and energy. This is chapter 2, part 2. You remember this, right? This is really basic. Reactants and products. Reactants are the substances or chemicals that are going into the chemical reaction, and the products are coming out. So sometimes, as in with a synthesis reaction, we have multiple reactants combining to form a single product. That's actually called anabolism in human physiology. This idea of synthesizing, building things up, is anabolism. Sometimes we start with a single reactant that breaks apart into multiple products, right? It really just depends on the direction of the chemical reaction in terms of what we call a reactant and a product. When we start with a larger reactant that breaks apart into multiple products, this is of course decomposition. And in human physiology, we're talking about catabolism. Anabolism and catabolism equal metabolism. So when I say metabolism, what do you think about? I think about my friend Tony. He has great metabolism, right? No matter what he eats, he seems to stay thin. What this really means is metabolism is like a ratio of how much building up and storing am I doing and how much burning and tearing apart am I doing. That's really going to tell me or tell the scale if I'm gaining or losing weight. So let's learn more about this idea. Here is a lovely visual. Anabolism, as in anabolic steroids, right? Here's Arnold Schwarzenegger, of course, back in the Conan days. Man, he is just buff, huge. Obviously, he spent a lot of time in the gym, and he's probably had some help building things up, right? Anabolism is a metabolic process where two or more reactants are chemically combined to form a new and larger one. This probably sounds a lot like synthesis, and as a matter of fact, in human physiology, synthesis reactions or anabolic pathways use a chemical process called dehydration synthesis. Say it with me, dehydration synthesis. Dehydration means the removal of water, which is what we see here. And synthesis means building two things into a bigger thing. So we're actually looking at protein synthesis. I'm going to use a pink amino acid and a blue amino acid, and I'm going to add them together. I'm going to take the hydrogen from the blue and this OH from the pink and form a new water molecule, which will leave the reaction. I mean, you can think of it as the product, but it's leaving the reaction. That leaves an unpaired electron here on the nitrogen and an unpaired electron here on the carbon. They combine to form a new covalent bond. Now, the other thing to think about in our metabolism pathways is that water and energy move in opposite directions. This is not always true, but in this class it is. Energy goes in and is stored in the chemical bond. Water goes out and we form this new dipeptide. That's what we call this product. So all of our macromolecules, whether we're talking about carbs or proteins or fats, lipids, and nucleic acids like DNA and RNA, they're all assembled this same way using a chemical process called dehydration synthesis. So that's how Arnold got so big and buff. He built up a lot of protein. How about this young lady? Very severe case of anorexia nervosa. Maybe this is photoshopped. I'm not really sure. It looks like this young lady is near to death, right? She is what we might call skin and bones. And the reason that she's so thin is that she has catabolized all of her fat, and as a matter of fact, most of her skeletal muscle, right? Look, there's no gluteus maximus. You can tell the organs are atrophied. Intercostal muscles And you can literally see the infraspinatus. There's such little subcutaneous fat, trapezius here. The point is, this young lady has starved herself, and so her body was unable to get energy from food, and so instead it got it from catabolizing, from breaking down her fats and then her proteins into smaller products, which release the energy to keep her going, keep her thinking, keep her heart rate and her body temperature up. So catabolism is breaking things down, and all of our catabolic pathways use the same chemical process, a chemical process called hydrolysis. So whether we're talking about carbs or proteins or fats or DNA, all macromolecules are broken down the same way using a chemical process called hydrolysis. This is in every way the reverse of dehydration synthesis. Look, we start with a larger product, we add water, energy is released when we break the chemical bond, and the products are smaller than what we started with. Where did the water go? Look at it, itself split apart. Hydrolysis really means water breakage, and you can see that in two different ways. The water's breaking the macromolecule, and water itself is breaking apart to give a hydrogen functional group to this glucose and a hydroxyl to the other one. So that's the basis of metabolism. A couple quick things before we finish this video. Redox reactions, I'm sure you know all about this from basic chemistry, but remember, oxidation is the loss of an electron and reduction is the gain of an electron. These redox reactions are really important in our metabolism as well. It's really how we transfer energy from the food that we eat into our physical body for storage or for use. Right now, great video here on slide number 29. All you need to do is download the PowerPoint and watch the video at your own leisure. Energy, the capacity to do work. What do we mean by work here? We mean like physics work. Energy making things move or making things change. And remember these: potential and kinetic, mechanical, chemical energy. Heat. We really focus primarily on these two in this class, although obviously the cardiac cycle and physical contraction of the skeletal muscle has something to do with these two. And adipose tissue, fat tissue, stores energy, so that would certainly be an example of this. But we're going to focus mostly on chemical energy and heat. Speaking of heat, look at this. When a chemical bond is broken and energy is released, we capture some of that energy to make a special molecule called ATP. It is our universal currency of energy, and all of our cells use ATP like a rechargeable battery. So look at this. We break a chemical bond and use some of the energy to form ATP, but a bunch of the energy is released. It's not captured and it's turned into heat. And so warm-blooded animals really are super inefficient in our chemistry, right? We are using a lot of stored energy and releasing it, but we're wasting most of it, and that's what keeps our bodies warm. Now, the interesting thing is it's turned out to be an advantage because through evolution, our enzymes and proteins have assumed just the right shape so that they can operate more efficiently at a higher temperature. So this is, of course, why if you go into hypothermia, you could get sick or die, right? It's going to change the shape of your proteins. Or if you have heat stroke and you become too hot, it could also change the shape of the protein. So we're designed to operate at just the right heat. We'll talk more about that in just a little bit. The last topic here, enzymes. Enzymes are biological catalysts. Remember that word? A catalyst is a substance that speeds up a chemical reaction, right? It makes it happen. And the cool thing is the catalyst can do it again. It doesn't wear out. It doesn't change. It just speeds up the chemical reaction. And so enzymes are the magic of life, ladies and gentlemen. Special proteins which catalyze or increase the rate of a chemical reaction to make it happen. So when you digest food, does it get digested faster than if you just left the sandwich on the table? Yeah. Why? What makes the sandwich fall apart faster in your stomach than on the table? Enzymes. Catalysts speed up the chemical reaction. Likewise, if I want to lose weight, I can't just wait for my fat to sort of decompose on its own. I need enzymes to break it down now so that I can release the energy within. Let's look at this. You might remember these from basic chemistry. These energetic graphs show us what we start with and how much energy there is, and what we end with and how much energy there is. And you can see here, this is what we might think of as an exothermic reaction, right? It's releasing potential energy. The thing that we're really focused on in this graph, though, is this part right here. If I start here, how do I get it to go over the edge? I have to add all this energy, significant activation energy, and it might not happen at all unless I cook it or heat it up or irradiate it. That's not an option. In my body, I can't cook my body or irradiate my body to make the chemistry happen. I need to lower the activation energy. This is the functional effect of the enzyme. Now, if I want to make it go from here to here, I just have to go bloop, just over this tiny little hump. And so we say that an enzyme lowers the activation energy. In English, I say the enzyme makes the chemical reaction happen. It wouldn't otherwise happen. In human physiology, if we're not irradiated or cooked, we're stuck at 98.6 degrees. So I can't add more energy. How do I make the reaction happen? An enzyme. And this video here on slide 34 is a great one. You should watch it at your own leisure to see how enzymes work. So here is a good time to pause the video and make sure that you can answer these questions before you move on.